This is Monday, January 11th, 2021, Physics CP. We're making up a problem for three electric charges in a row. The problems we've come up with is the first charge, Q1, is positive 5.00 coulombs of charge. 67.0 centimeters to the right of it is charge Q2. Charge Q2 has a magnitude of negative 3. I'm sorry. Charge Q2 has a value of negative 4.00 coulombs. And 6 centimeters to the right of charge Q2 is charge Q3, which has a value of negative 3.00 microcoulombs, where micro means times 10 to the negative 6th power. I think I would like to take the trouble to calculate the net force acting on Q1 and then maybe do the net force acting on charge Q2 afterwards. Maybe even on Q3. Maybe we'll even do all three of these as an exercise. And how do you do this? How do you do it correctly? All right, so we're going to be using Coulomb's law for every pair of charges. And it states it's the product of Boltzmann's constant lowercase k times the magnitude of the first charge, I'll call it QA, times the second charge, I'll call it QB, divided by the distance between A and B squared. Q has to be expressed in units of coulombs. R has to be expressed in units of meters, not centimeters. K is Boltzmann's constant that has a value of 8.99 times 10 to the 9th power newtons meters squared per coulomb squared. There you go. So the process I'm going to do is to first find the net force on Q1 by shutting off Q3 and calculating the electric force acting between Q1 and Q2. So the force on Q1, I'm going to write this as the force of Q2 acting on Q1. So I'm writing F21. The force of Q2 pushing or pulling on charge Q1 is equal to K times 5 coulombs times negative 4 coulombs divided by, I have to take the 67 centimeters and convert that to meters, knowing that 100 centimeters by definition is exactly 1 meter. 67 centimeters would be 0.67 meters. So that's what I'm going to plug into here, 0.67 meters, quantity squared, and power up my calculator. I had stored the value of K on my calculator previously. So on my calculator, I go alpha K times 5 times negative 4 divided by 0.67 squared, enter. And it's very hard to see, but that's a decimal point here. I get negative 4.01 newtons. The calculator actually says 4.00534640. Oh, ha ha ha. I missed this last part. Times 10 to the 11th power. That's pretty important. Times 10 to the 11th power newtons. Woo! Okay, so that is a very, very, very strong force of electrical attraction. The minus sign means it is attracting it, and so it is pulling to the right, caused by Q2. Q1 is positive, Q2 is negative, opposites attract. So this is the force of Q2 acting on Q1. I shut that off. Now I want to calculate the force of charge Q3 acting on charge Q1. Into Coulomb's law, I would plug in K times charge Q1, which is 5 coulombs, times charge Q3, which is negative 3.00 times 10 to the negative 6th power coulombs, because that's what micro means. Micro means 10 to the negative 6, and divide that by the distance from Q1 to Q3 squared. Well, first I go 67 centimeters, then I go an additional 6 centimeters. So the total distance is 73 centimeters. I convert 73 centimeters to meters by dividing by 100 and square it. Alpha K times 5 times negative 3 times 10 to the negative 6 divided by 0.73 squared. Huh. I get negative 253,000 newtons. Again, with the minus sign, it is pulling it to the right. It is an attractive force. Now, in scientific notation, this is negative 2.53 times 10 to the 5th power. This is 1/1,000,000th, slightly less than 1/1,000,000th of the force of the top guy. But strictly speaking, we would add them together and say, oh, the force is, well, my calculator is going to show this doesn't even change. But if you like, I can type it in and say, what is this plus negative 4 times 10 to the 11th? And it doesn't change it. That was still 4.0053. So no change. It's still 4.01 times 10 to the 11th power newtons to the right. So in words, this charge to the right is 1,000,000 times weaker than the charge Q2 that is close to it. In addition, it's even farther away from Q1 than Q2. And the farther the distance, the weaker the force. So this is weaker by more than a factor of 1,000,000. When we add this very weak attractive force to this incredibly powerful one, relatively, the powerful one dominates it to 3 sig figs. We don't even see any effect caused by that guy. Now, I'm going to change the problem. None of the values, but just the location for the net force. Instead of finding the net force on Q1, now let's calculate the net force on Q2, the middle charge. Okay, so you need to have a sketch that you can refer to keep it straight which one goes what way when you calculate the result. So we're going to find the force of charge 1 acting on charge 2. Newton's 3 laws of motion include the third one that says, for every action force, there is an equal and opposite reaction force. In other words, forces always act in pairs. If charge Q2 is pulling charge Q1 to the right with a magnitude of 4.01 times 10 to the 11th power newtons, then charge Q1 is pulling charge Q2 to the left with a force with a magnitude of 4.01 times 10 to the 11th newtons. I have a pen cap, and if I pull on it to the right with my right hand and pull on it to the left with my left hand, the pull of one hand against the other is always equal. So if I'm pulling to the right, 10 newtons, then the left hand is pulling to the left with 10 newtons. And you're saying, well, why does it move? Well, that's a different question. The point is, by Newton's third law, if I'm pushing this guy to the left with 20 newtons of force, this guy is opposing that push with 20 newtons of force. Now, he might lose this tug of war relative to the outside world, but for every action force, there's an equal and opposite reaction force. Even if my hand's not there, if I push on this empty pen cap and 1 Newton makes it move, the pen cap is pushing back on my finger with that same 1 Newton of force. That means once I had calculated the force of charge Q2 acting on charge Q1, that also gives me the magnitude of the force of charge Q1 acting on charge Q2. But look at the geometry. Q2 was pulling Q1 to the right. So Q1 is pulling Q2 to the left. And here I could say it is 4.01 times 10 to the 11th power newtons to the left. Now I'm going to calculate the force of Q3 acting on Q2. So force of charge 3 acting on charge 2 is going to be K times negative 4 coulombs times negative 3 times 10 to the negative 6th power coulombs divided by, now in this situation, the distance between them is small. It's 6 centimeters, which in meters is 0.06 meters. So this is going to tremendously increase the force between Q3 and Q2 relative to the force between Q3 and Q1. All right, so I power up my calculator and I go, what is alpha K times 4? I see I have 2 negatives, so I'm not even going to bother saying it. Times 4 times 3 times 10 to the negative 6th power divided by 0.06 squared. Beep, beep, beep. And the number goes up. Okay, it says this is equal to 3.00 times 10 to the, let me count it, 1, 2, 3, 4, 5, 6, 7th power newtons to the left. And why is it to the left? This one is positive. The previous one was actually negative on the calculator. But the difference is the geometry. Negative means it is attracting it. Q1 was pulling Q2 to the left. positive means you're repelling. Q3 is pushing Q2 to the left. So both of these forces end up being to the left. Even though your calculator said this was a minus sign and this one's a plus sign, the geometry says, oh no, they are both going to the left. So 4.00533464 times 10 to the 11th plus the previous answer. It still wasn't significant enough. The net force worked out to be 4.01 times 10 to the 11th power newtons to the left. It finally made a small difference somewhere out in I don't know, way out there. 3 in the 1, 2, 3, 4, fifth decimal place. It finally made a small change. It went from 53 to 56. Okay, so there's the answer for what is the net force on the middle charge caused by the two surrounding charges. And I think for completion, I will now calculate what is the net force acting on a third charge. Because we've really done all the math already. It's just looking at what we've done and figuring out what we do with those numbers. So we need the force of charge 1 acting on charge 3, and add to that the force of charge 2 acting on charge 3. Well, so here we go. Q1 and Q3, we already calculated that force was negative 253,000 newtons. The minus sign means attracting. So this is 253,000 newtons to the left because it's pulling Q3 towards Q1. They're opposite in sign. We've already calculated force of charge 3 on charge 2. That is 3 times 10 to the 7th power newtons. To the left. Yeah, okay. So this is 3,000,000 newtons to the left. Now we can see these are not way, way, way different from each other because Q1, although it is stronger than Q2, 5 is greater than 4, it is much farther away. I'm wondering if I'm doing this right or if I'm making a mistake. I think I'm doing this correctly. Oh, 3 times 10 to the 7th power. I wrote this as 3 times 10 to the 6th power. My bad. This is actually 30 million. There we go. Now it makes more sense to me. 30 million is 3.00 times 10 to the 7th power. 1, 2, 3, 4, 5, 6, and one more. Now I can add these together and it makes sense to me. The net force would be 30 million. And now, haha, to 3 sig figs, this 253,000 rounds up to 300,000 newtons to the left.